So what is the fundamental that's going on underneath? So basically, you could represent the environment as a Markov decision process. So how many people here understand Markov processes or Markov reward processes? Great. So essentially, so just ignoring this, imagine a deterministic system where the state transitions are well known in a system. Like one would do, if you have electronics background, then you make state machines, that how a chip works, right? Versus a real life system in which the state changes in a stochastic fashion. So basically your model would have states which are S0, S1, S2. Each state you would have certain actions, A0 and A1, right? When you take an action, there is a certain probability that you go to the next state, right? So if you take at S0, you take action A0, there's 0.5% probability that you go to S2, or there is also 50% probability that you stay in S0. So obviously the probability sum to 1 in a fully defined system. And if you take A1, there's a 100% chance, which is probability equal to 1, that you'll actually go to S2. So Markov decision processes are basically systems in which the probabilistic transitions from states to another states are governed by these probabilities that happen post an action is taken, right? And there is a reward associated with every action. The rewards are typically deterministic. If you take this action, there's a certain probability you go to the next state, but you get a reward. In other cases, you can say if you take this action, there's a certain probability you get this reward. Both cases get modeled over here. So how does the whole, if there's an episode, basically you go from one state to a terminal state Sn, right? Then what does it look like? You are sitting at a state S0, you start in a state S0, first starting state, right? Which can be arbitrary for example. You take an action, get a reward, and you go to the next state. In the next state, again make a decision. The robot goes to the next state, the next grid point, again takes an action. It takes an action with certain probability, it moves forward, it moves to the right, and gets a reward, which is specified on the grid as the immediate reward. So this is what an MDP is. The major components that an agent or an RL, a reinforcement learning agent, would play would be the policy, which is the agent's behavior function. Policy basically means it's a mapping from state to action. What action should I take in every state so that I maximize my reward, which is the future discounted reward as I go through and reach my terminal state, right? In a simple Atari game, for which I'll give an example, it is what's the total reward, what's the maximum score I can make, and can this program beat a human being, right? And so forth. So that's a policy. The value function is how valuable is each state or a state and action. So basically, the reward says I moved from here to here, this is the reward I got. The value says the value of this state in the context of the total system is basically so much, which means the long-term reward I will accumulate by sitting in this state is the sum of the discounted rewards from here going all the way to the final reward, right? So it's kind of a tactical and strategic trade-offs that you make in real life, right? It's basically the immediate reward is so much and you are happy you got this reward, but look, you took this move in a traffic where this was an empty road, but going forward it was a totally jammed set of interconnects in between to the target, whereas you had initially you took a hill climbing step, you took a jammed road, but after that it was a smooth ride all the way to the target, in which case the total time was much lesser, in which case the reward is higher than going through this particular route. So the trade-off or the difference between value and reward essentially goes across immediate versus the strategic, which is the value function. The model, which is the agent's representation of the environment, is essentially what is the probability, what are the states and transition probabilities that the agent can infer about the environment, right? So in a robot case, in kind of artificial examples, these probability transitions are given to you. You formulate it as a planning problem in which we typically use dynamic programming. You solve the thing and you achieve the end state and you say, okay, I'm done. Right, I've gotten the best answer, game over. In real life problems, that always inferred. So the model basically is whatever the agent can represent of the environment. This is one example that I've been giving. So you have a start state for the robot, you have an end state where you get a +1, you also can get a -1, let's say it falls in the pit. In the intermediate rewards, you can have a -0.04, and this is the probability. So if you take an up move, you can move up with the probability 80%, but then you also have left and right moves. Imagine there's a wind blowing, and then wind can shake the robot here and there. So even if you took the step here, with 10% probability the robot gets moved on the left side or the right side, because there is a wind which stochastically changes. And the system could be non-stationary. So basically, in some cases, the probability distributions of how the environment is, right, it is stationary. So imagine So if I give you the reverse example, a stock market, essentially it changes in all the different the huge number of variables that impact how these probability of making money or how these stocks will vary, they don't remain constant. The underlying time series have changing means and variances. So basically it's a non-stationary distribution. In most of the real world problems, it will be non-stationary underlying distributions. So you really need to have an algorithm which works in a practical way, which handles the underlying non-stationary environments. So value function, as I was mentioning, essentially you have future reward, which is a set of rewards, and typically what you actually end up considering from the time t, from this time onwards, where I'm sitting at this time at this state, what is the total reward I get to the terminal state. In case of Atari games, I have played the game for 10 minutes. When I actually end up ending the game where my the life ends, then basically what's the total score I have made versus a human versus a computer and so forth. The discounted future reward gets multiplied by a discount factor, which essentially models the environment is stochastic and is useful in many such contexts. So that's a typical modeling function that we use. And a good strategy essentially is to choose those set of actions which maximize the discounted future reward. So the RL, reinforcement learning landscape, has huge number of techniques. I'll cover just some of them and give concepts of how these things work out. Essentially you have policy optimizations, which can use evolutionary algorithms like genetic programming and so forth. Or you can have policy gradients and actor critique methods, which are a combination of the value iteration and policy iteration techniques. So a typical introductory course that you would go through essentially covers these topics, policy iteration and value iteration, right? And the new techniques that have come over here are essentially, they had been existing in the past, but recently when essentially you look at high dimensional problems and high dimensional actions, high dimensional state problems and continuous action problems, like imagine you are flying a helicopter, a computer is flying a helicopter, then you need policy gradients as they are more effective versus these kind of methods which actually give the value to each state and try to model the underlying states of the system in a more interesting fashion. So coming to now deep reinforcement learning. So essentially this is what is happening over here. So you have an agent which is playing the game. This is the DQN network which is playing the game. It takes an action. What do you take as an action in an Atari game? You move the joystick. There are 18 positions in the joystick, for example, right? And you are playing all these different kinds of 80 to 100, whatever number of Atari games exist, right? This is the simulator of the Atari game, right? Which essentially says if the agent takes this particular action, then what happens to your total score, which is coming over here, right? So this environment, right, essentially gives the agent the reward, and then it takes the agent to the next state. Basically, as you are playing the game, something hits, or your this particular agent dies, or the player here dies. For example, it has a next life. Then the actual image changes, right? So what this agent has to learn through the images, it has to build the states, right? So now, if you look at this is basically a video sequence. So essentially, as these movements are happening, you need to collect a sequence of frames so you can say which state I am, right? In this particular case, in what direction are these moving, right or left, right? In a case of bricks, essentially what direction is the ball particular moving, what angle it is moving, it's moving up and down. So basically you have to take a sequence of frames and infer a state. When you infer a state and you have a set of states that you have observed, remember, there is no model that is given to this particular agent of what this simulator is actually doing. So this guy has to build all those set of states. For each state, it knows the action that it has to take, the 18 position of the joystick, and then it has to assign value to those and then decide what is my next action that I'm going to take at this state so that my total score gets maximized. So this is the first breakthrough that the DeepMind team, David Silver's team, had. And this is the fundamental algorithm that they use as the base algorithm. Obviously, they did enhancements on this. This was known quite early before that. So essentially, what is happening here is that at every state, you have these actions. For every action, you have a reward, and then you have a probability of going to the next state, which are the S primes. So what you do is a fundamental dynamic programming derived step. Essentially, is you update the Q value for the time t+1, given the current state and the action that you take, by the old state, the value in the old state, plus a learning rate, which is a typical function we use, a typical parameter that we use to tune, into the immediate reward that you get by taking that action, plus whatever the best you could do, right, as the reward for the next state. which is the maximum over all the actions you could take in the next state, and then whatever the increment you got over this particular value at the current point before taking this move, right? You take this difference, multiply by the learning rate, add to this, and that gives you the updated value of at this state taking this action, what is the new value. So using these iterations, basically what you are able to do, using this kind of alpha learning rate, you are able to model a non-stationary environment to a limited extent. Basically, if you, in an Atari game, the things are more or less stationary. In real life, for example, in stock prediction or in other kind of cases, where the things are determined by the economies and the various states in the economy, which are governed by all kinds of factors, as you are aware of. So here, if you visit the same state, if you visited the state for the first time, you have a certain probability distribution, or you infer certain probability distribution of transitions from one state to the next state. But if you, after some number of moves, you visit the same state, the system is non-stationary. These probability numbers have changed, right? The probability that when you take an action, you move to the other states, these numbers have changed. If these numbers have changed, then you put an alpha learning rate, which essentially determines that whether you can update your, a new value. Obviously the state transition probabilities have changed, your value has changed, so you have to update it, and you use an alpha rate to make sure that that update keeps on happening, and also this alpha has to be set or decayed over time so that you converge to a policy. So essentially, what is the challenge in playing the Atari game, right? So as you could see, this is the whole image of the underlying environment that you are modeling, right? So if you take an image size of 84 cross 84 pixels, right, and you take 4 consecutive images, how the video is flowing through, so that you actually are able to recognize that state, right, and each pixel gets represented by, let's say, 256 gray levels, then you could see it is 256 to the power of 84 cross 84 cross 4, because that's the number of pixels of which you are basically modeling. That's basically one particular frame, and these are 4 frames that you are modeling. So essentially in the Q table basically, as you saw, essentially it is Qt plus 1 st comma at. So essentially you are keeping a table, what is the value of each state, and essentially you are running a dynamic programming type of iteration on that particular state, or synchronous backups or asynchronous backups on that particular state. So you need to have so many rows. These rows basically cannot be modeled. And before deep learning came into existence, this is exactly the point at which reinforcement learning was totally stuck. It was not being used in any of the practical problems, other than very few of them in which you could actually abstract out the states in a certain way. The system actually could be solved in a meaningful fashion. So there were some early wins, like in TD Gammon, where success was obtained using reinforcement learning, but because there are a huge number of states over which you want to model your value function, these things were totally stuck over there. So with deep learning, people basically figured out that why not estimate this value function. This value function is basically you are estimating. You actually never know the truth, because the underlying system, no one can tell you. No one will tell the agent about that. Whatever is the simulation is happening in the Atari game, whatever is the environment through which the helicopter is flying through, no one is giving you a full physics model of what is going to happen. So the agent, without that knowledge, has to learn. What does that mean? Has to learn, has to estimate. So what these guys did was, they said that, okay, why not estimate this value function through a neural network? And neural network, the best forms of representation learning and also highly nonlinear kind of representations are deep networks. So in a nutshell, this fundamental idea was coming through function approximation. So there were a lot of techniques people had figured out earlier with linear function approximation, nonlinear function approximation, but without the deep networks being there, this kind of effectiveness was basically not there. So what they essentially did was, they in one kind of implementation, they fed the state and the action through this deep network. This is a typical deep network that we saw in the earlier slides, which are your RBMs and autoencoders, or typically CNNs and LSTMs. They're all different kind of RNNs and all this kind of deep networks. And basically it will train a Q value. A Q value is essentially trained, so you know for a certain set of, when you train the network, you say basically if you at a state you take this action from the known training data, you can assign certain value, and that's basically you will propagate backwards to train this particular neural network. And this basically got evolved into a state input, which is the state that is inferred in Atari games by the sequence of the 4 frames of the video, gets fed into the deep neural network and gives you these many Q values as the number of actions. So there will be 18 such values for the Atari game in particular that you are playing. And essentially what you are doing is, you introduce a parameter theta, and you have a nonlinear queue network, which is basically a deep queue network as it is called, and essentially it is an approximation to q star s comma a. So this avoids completely building a table which is highly large or really exponential in size, which basically is much more than the number of atoms in the universe. So this is what an architecture looks like. You have an end-to-end learning of values, which are the Q values for every state and every action from the pixels that are given. The input state S is basically a stack of raw pixels from the last 4 frames. The output essentially is the value function for all the 18 joystick or button positions, which is coming over here. So what happens is that you get this 84 cross 84 image of the video. That is how the game is playing. You have 4 such sequences that you consider that these people found out sufficiently represents the state on which you want to make your moves, right? Then you pass it through CNN layers, convolutional network layers. You apply certain filters of certain sizes with certain strides. As I was mentioning, how this convolutional network works essentially on a particular input image, this is the size of the filter. You go through these multiple layers. Finally, you have fully connected layers, and here you train a softmax classifier on which you say what should be the value of the particular state comma action. So this is what the deep queue network looks like in a more high level diagram. So here essentially you have 18 such outputs, right, which essentially give the value of each action given the input state that the system observes, which are the 4 particular sequences of frames in the particular video. So it has 3 convolutional layers and 2 fully connected layers, and this was published in 2013 by Mini and team. So here are the results of Atari, and that's where the magic is coming from. And as you can see over here, these are all the different games of Atari, right? These are percentage levels of performance compared to a human. This essentially blue represents the score of a deep queue network, which is the work of the DeepMind team. And here essentially is a change point where we are saying all the numbers here are either close to a human or essentially they are way more than a human, right? When human, basically it's one of the best numbers that they could get as a player and compete with it, or one of the best scores that they could observe that a human could do. So with such a kind of architecture, which in deep reinforcement learning combines the power of estimation that a deep network provides and a reinforcement learning algorithm, now we are able to beat humans in these games. And as you would see, we as humans also are playing as a reinforcement learning algorithm would play. We would never try to calculate at the back of our mind the physics, the full physics that is going in playing an Atari game kind of a system. We would have just approximate ideas about what the acceleration and the velocity of the angles of the balls are and how we should make the particular moves on the action that we need to do. So this is another representation which essentially, another work which essentially takes the idea of DQNs and makes it massively parallel, and it achieves 10x faster than the DQ network. This is a technique which essentially uses asynchronous advantage actor critique methods. So these are basically methods. So in DQN, essentially you use a value iteration and you use an off-policy learning and you use a neural network to model these things or estimate the particular value functions. In these kinds of methods, they use policy gradients, which was the next thing that I mentioned in the agenda, where the policy is explicitly estimated. What is the policy? That given an action, given a state, what is the probability that you take an action, a particular action? So you specify across all possible actions, which can be continuous space or a discrete space. You basically model this probability, and then you basically parameterize this particular probability function, which is pi of a given s, and then based on this you consider your loss functions and the kind of progress you are achieving as the game moves forwards. So this is a method that derives essentially from there. It goes one step ahead, in which it uses the policy gradient techniques. As you would remember the reinforcement learning landscape slide that I had earlier, it would take the policy values, explicit policy evaluations from the policy gradient techniques. It will use the value estimations using the deep queue networks. So it will have a policy network or deep network that estimates the policies. It will have a deep queue network which estimates the values. It takes the power of both, right, and essentially reduces variance using these advantage functions. It uses asynchronous methods to do these updates, and then achieves solid performance on some of the games that I'm going to mention. So this is a labyrinth game, and let me show you a video of this. So here, as you are seeing this, you have to navigate through this particular grid. If you get the green apple, you get a +1 reward, which is mentioned over here. As the reward is increasing, right? You see 3, 4, and so forth, right? So the system essentially has to keep track. The system only sees this grid. It doesn't see a full picture of the grid also. There's no full picture that the system has, no map that the system has. The system builds the map in its memory by just transitioning across or moving across this maze. It gets reward as it catches this green apple. It has to plan and do a model-free reinforcement learning algorithm to achieve this. So what is happening in this game, right? It uses these methods which combine the policy networks and the value networks, right? Essentially, it uses an underlying LSTM and CNNs to represent what the state is, right? And then it emits these numbers, right? Pi of a given st minus 1 essentially is what is the probability that I should take this action given the state. So if I have a higher probability of taking an action given a state, that is the direction I will move. If I have a lower probability, then essentially I might take that action. If I take an action of lower probability, that means it is not the best thing I needed to move, but I explore my system. So that is what is essential in reinforcement learning algorithms, that you do an exploration and exploitation trade-off. In an exploration trade-off is, okay, this much as I know the system is a black box to me. This much I knew about the system while I did some trials and errors. Can I learn more about the system and then choose the best action, or should I just take the best action and just move over there? Right? So that is how you move in a typical life. So that's an exploration-exploitation trade-off. So what is happening is you are doing an end-to-end learning of the softmax policy pi of a given st from the pixels, right? The pixels immediately get converted via CNN into a representation, which basically becomes your state, right? So this whole thing, which seems daunting at first on how a computer could address this, immediately using a CNN gets represented over there. The observations are the raw pixels from the current frame, right? And the state is observed through an LSTM, right? And then both the value functions and the softmax over the actions are essentially emitted by this particular deep networks. So here is another example where the human motion is modeled by this is a physics simulation program, right? So this is a simulation program which models these kind of humans or modeling of entities moving. They have certain joints. The position of the joints, the angle of the joints, the speed and the force at which, or the torque at which they have to take the next move across all their body parts are the set of actions that this system has to take. Based upon the action that is given to it, the system will simulate. This particular program will do a full multi-joint dynamics with contact, kind of a full physics simulation using partial differential equations, and give you what is the next state. So basically, if you ask this guy or give this simulator an input which is not the correct input, it lifts its leg and turns like this, it actually is going to fall to the ground. Right? So those are the trial and error that the reinforcement learning agent, the brain that you had in the earlier diagram I was showing you, basically needs to make those moves. So this whole thing, this whole system rather, is a freeware. It should be an open source project that is released by a university that allows you to do real time physics simulations. So what is done over here is that the physics simulations are simulated by this Mujoku software. Right? What we need to do is to build a reinforcement learning agent or a deep reinforcement DRL agent that can do an end-to-end learning of the control policy given the raw pixels. The raw pixels are actually the images that you saw of the system or the particular entity that's trying to move in a particular grid. So you have the input state, which is a stack of raw pixels, which is the last 4 frames. Right? There are 2 separate convolutional nets which are used for Q and pi to estimate these values. These are 2 separate nets. The first net estimates Q, which is the value function. The second one that estimates the probability of taking an action given a state. Right? They go through this convolutional nets and find the fully connected layers. They get trained using the softmax function, and the policy pi is adjusted in the direction that improves the Q. So you basically use both these values, right? The policy and the Q, and the way the algorithm works, the DRL algorithm works essentially is you change this gradient, which you change these probabilities so that you can change to a higher value function. You can achieve a higher value function, which is this over there. So here is a Mujoku demo, which will be interesting to see. So this system, this particular point has to move in such a direction that this stick does not fall, right? So it is learning to do that. In here, a biped is learning to move as fast as possible on this particular way, and here are all these joints and the angles in which they're supposed to move so that it can move in the fastest speed and keep stable. Here a four-legged animal or a spider, as you can see, has to jump across, and it has to control all these actions to be able to do that. And here again is a different dynamics of another entity which is trying to move, right? So if you have seen the demos of Boston Dynamics on the net, you would see those weird looking buffalo type creatures which move, and these are the algorithms which are running behind those. I would strongly encourage to look at Boston Dynamics videos and how they look at. So this is another different objectives that, or different things that it's going to solve. So here this robotic arm essentially is learning to lift and place this thing over there, right? And essentially behind the scenes it is mapping these videos to states and then converting to actions where the policies of how to move in at any point is essentially determined by these algorithms. Okay, AlphaGo, the most interesting one. So how many people have heard of AlphaGo? Great. So this is a very challenging game. It is much more challenging than chess, and essentially the idea is to get the maximum. Basically, you end the game when the particular coins that you have end up, and you get the maximum entity or maximum area on this particular board.